David is very kindly giving us a 3-day series of lectures on cognitive architectures. Both yesterday and today, it's module 6 of his course. Yesterday we had lecture 1, today will be lecture 2 with some examples on cognitive architectures, and I think David will also talk a bit about the Common Model of Cognition. So let's see how today goes in terms of security and bots. I hope it will be less exciting than yesterday. In any case, I think possibly soon after the meeting I will mute everyone so that we avoid any incidents. But in any case, if you want to ask a question, there is the chat, and you can also raise your hand. I will be keeping an eye on the participant list. And that's roughly all from my side. So David, the floor is yours.
Okay, thank you very much. Welcome back, everybody, and welcome to anyone new that's joining. Congratulations on having survived yesterday. It wasn't I'll call it a class because that's what it was, that I was particularly looking forward. I never enjoyed teaching that material, but it's essential to at least cover it because it gives me the vocabulary and the foundation on which I can build. But today, I'll try and provide a little bit more excitement of my own by taking you through a tour of some cognitive architectures. So today we're going to look at some examples, and then we'll finish off looking at the Common Model of Cognition, sometimes referred to as the Standard Model of Mind. So what we're doing today, that my strategy over the 3 days is to pursue this policy of progressive deepening of our understanding. So yesterday was broad and quite shallow. Today I'm going to have, you will see 2 levels of depth of abstraction. I'm going to cover 4 or so cognitive architectures at a fairly shallow level. And then I'll pick one of them and I'll cover that a little bit more deeply. And that gets us into, or gets us ready then to take on tomorrow's work, where I'm going to spend the entire class or the talk talking about the CRAN cognitive architecture. So that's where we're going. As Anna mentioned, all of these notes that I'm going through today are part of a course that I've been preparing, and which will be made available thanks to the funding of the IEEE Robotics and Automation Society. So this is the material that we'll be covering today. This is what we'll be covering tomorrow. And the takeaway message from this slide is there's a lot of other lectures available. And I woke up this morning conscious of the fact that yesterday I jumped in the middle, module 7, module 6, of a pretty extensive course on cognitive robotics. And I didn't even have the foundation of going through all of the material I would normally go through in terms of artificial cognitive systems and cognitive science. And this is a course on cognitive robotics. So this is even just a light version of artificial cognitive systems. So if you're interested, you can have a look at that. And you can also perhaps look at lecture 1, which introduces the discipline. And it's in a sense, it can be helpful because the definition of cognition, the definition of cognitive architectures, obviously, or cognition and cognitive robotics, obviously impacts on how we define and view a cognitive architecture. If you're hungry for something even in more depth, there's another course which pursues these issues in a little bit more in more depth with at a slower pace and dividing up. So, for example, there's material here on embodiment and autonomy that we don't cover in cognitive robotics. And bearing in mind the questions yesterday, perhaps I should. But with a limited amount of time, we'll carry on. Before I begin today, I thought I'd take the opportunity to extract 1 or 2 slides from the artificial cognitive systems material, because they will give me the basis for the material we'll be looking at in cognitive architectures. In particular, we mentioned memory yesterday, was in that landmark survey of cognitive architectures, the recent one by Yulia Katsuruba and John Tsotsis, which really has become the benchmark survey now in cognitive architectures. They had 4 different types of memory. And I thought it might be interesting and instructive just to put up a very simple And I emphasize engineers' perspective on memory, and distinguishing a taxonomy between short and long term. The fact that we've got declarative and procedural, and declarative arguably can be separated into semantic and episodic, and working memory is a component of short-term memory. But of course, it's not quite as simple as that, and there are other types of memory you need to be aware of as well, including hetero-associative and auto-associative memories, because they're used in cognitive architectures, and the difference between modal and amodal memory. We mentioned yesterday when we talked about Lawrence Barcelou's work on grounded cognition. And I can't resist using this slide to emphasize that memory isn't retrospective purely, it is also prospective, it's forward-looking, and it's future-oriented. And that's captured nicely in this quotation from Lewis Carroll's Through the Looking Glass. It's a poor sort of memory that only works backwards. I had this in a slide in a talk I gave in Linköping a couple of years ago, and as soon as I said it, Tom Zemke, who was in the audience, shot back at me, and he says, and it's a poor sort of memory that only remembers what's actually happened. And we all laughed, of course, because it was a very insightful comment, and he's right, because memory is also constructive. And this is something that we know about episodic memory in particular, that it is reconstructed every time. So the memory that you have of your childhood, or the good times or the bad times, are not actually what happened. They are biased towards the onset of events, and they're biased towards the good things and the bad things. You remember the best and you remember the worst. You rarely remember exactly things as they were. So you reconstruct your memory. So this is something we have to be aware of as well, certainly in terms of natural memory. So with that said then, Yannis also quite rightly pulled me up on a number of things about embodied cognition. I just wanted to expose you to this definition here from the Stanford Encyclopedia of Philosophy, just highlighting the fact that by embodied cognition, we mean that the agents beyond the brain body plays a significant causal role or constitutive role in cognitive processing. And Lawrence Barcelou, in his really nice book on embodied cognition, then has these three different hypotheses. The conceptualization one, which effectively says that your body in some sense filters or constrains or conditions your cognitive processes and what you can cognize about. The constitution hypothesis, which is what we just said with the embodied cognition thesis, in fact, that the body is part of cognition, and that cognition is distributed between the neural and the non-neural. And then we have the replacement hypothesis, which says, in fact, that real-time interaction with the environment replaces the need for representational processes. And they're replaced by what? By dynamical systems-based perception action couplings. And so these are the different strengths of embodied cognition. And we mentioned as well the idea that people use different words to mean the same thing, and different things, they get mixed up. And we wanted to just give you this short explanation between the difference between situated, embedded, grounded, extended, and distributed. And embodied, as we saw yesterday, it depends on your interpretation. The important thing that's here is there's a version of embodied cognition which involves the environment being part of the cognitive process. And that's extended or distributed cognition. So it's body and brain for both embedded and grounded. This turns out to be important because what I have not said anything about, and I'm probably going to say very little in the remainder, is the importance of the environment and the fact that cognitive systems evolved and operate in an ecological niche, and that they are tuned to that particular ecological niche. And so your cognitive capabilities reflect the niche in which you operate. And that's something that we don't often address when we design cognitive architectures. It wasn't mentioned once yesterday in this idea that how do you factor in the fact that there are inherent constraints, perhaps through the lawfulness in the environment in which, or the lack of lawfulness perhaps, in the environment in which you work, and how that can condition what is necessary in a cognitive architecture, and how it conditions the models that you build and the nature of the way that you build those models. So this is something that we didn't mention, and I have to say thank you to Yannis in a conversation by email after yesterday for flagging this to me, and he hinted at it in his question, and he made it explicit in a paper he sent me. So thank you about that. And then this is Lawrence Barsalou's, his focus on grounded cognition. Okay, so with that short preamble, just to kind of set the scene and give me a little bit extra to work with today, let me now get straight into the material for this afternoon, which is an overview of some example cognitive architectures. Now, there are many surveys out there. I've been responsible for one with Klaas van Hasten and Lucian Fadiga in the book we wrote. Giulio and Giorgio and myself had another one with 14 in a paper in the IEEE Transactions on evolutionary computing. But you really can't beat Julio Katsuruba's and John Satsis's recent survey. It is pretty much the definitive one now. The one thing that I will just observe here is that it doesn't have individual summaries of each individual cognitive architecture. In this particular one here, there's a page and a half summary of each of the 20. So you get a kind of a precise of each one. That's not the route that was taken in this particular survey. Rather, they survey them and see to what extent these architectures exhibit the core abilities that I mentioned yesterday that are in cognitive architectures. So that's the approach that they've taken. So you won't find, for example, an overview of SOAR or ACT-R or Icarus or Clarion or CRAN, but you will see how those architectures reflect the core abilities of cognition. So there are 3 paradigms of cognitive science. There are therefore 3 paradigms or 3 approaches to cognitive architectures, the cognitivist, which Katsuruba and Satsis refer to as symbolic in their review, and many other people do too. The term cognitivist, I was one of a reviewer of the 2014 book, pleaded with me and the editor not to use this word because it's such an ugly word, and I had to point out, well, I didn't invent it. It's a word that is used. It's not a particularly attractive word. And more today, people talk about symbolic. But be careful, because there are more entailments in the cognitivist tradition than in just the symbolic. I don't think you can see them as being purely identical in the sense of cognitive science. In terms of cognitive architectures today, yeah, they're pretty much, you can use it as a synonym. So they're the 3 that we'll be looking at. And what I'll do today is I'll sample them. So this is a picture, a diagram taken from the Katsuruba and Satsis survey, and it's a lovely illustration of the diversity, the number of cognitive architectures that exist, and divided into the emergent, hybrid, and symbolic, and with subdivisions then in the emergent and in the symbolic. And I'm going to sample just a few of the more well-known cognitive architectures, just so that you're aware of these, what are actually pioneering cognitive architectures in the field. And we'll start with perhaps the best known one of all. I say perhaps because there's ACT-R is the other one, which is very often comes to people's mind when you talk about a cognitive architecture. And I'll mention that too. Both, curiously, were both developed by researchers in Carnegie Mellon University. This is another interesting picture from the survey. So from now on, I'll just talk about the survey, meaning the Katsuruba and Satsis survey. And this shows the length of time that these cognitive architectures have been in development and when they were stopped being developed. And the takeaway message from this is a long time. So SOAR goes back to 1983 when John Laird started as a graduate student in CMU, and Paul Rosenblum working with Alan Newell. So SOAR, in a sense, is Alan Newell's candidate unified theory of cognition, which we mentioned yesterday. It started in 83. It's still going strong. It's in version 9.6 at the moment. It's a production-based system, and that means that it's a rule-based system. It operates on, effectively, if-then-else operations. And it operates in a cyclic manner. It's got what's called a production cycle where it takes all these rules and it sees what conditions match the information in the symbolic working memory. So based on what's in your symbolic working memory, that will allow a rule to fire. And because of that, you update your memory, that the then part of the if then close. And because memory changes, more rules can fire. So it carries on, lets all the rules fire, and then enters a decision cycle where it selects an action. It uses a concept called universal subgoaling. So when it can't select an action, when it doesn't lead to a new state, when the decision cycle doesn't lead to a new state, it then creates a new goal and exposes more knowledge. So not being able to progress is called an impasse. And so when you resolve your impasse, effectively you have reached this new goal, with the goal being to resolve the impasse. And what you have learned in doing that is then encapsulated in a new rule. And that rule is then stored in your procedural memory up here as a new production. And that is how SOAR classically used to learn. It was a technique called chunking. So to chunk meant to learn a new rule and to then store that in your procedural memory so that you could then use it the next time you encountered that set of circumstances. So that's SOAR. Now this is a picture of SOAR, which from SOAR 6, which is, if memory serves me, about 1996 and 97. And there's a summary of SOAR from that era in this survey that I mentioned, the first survey at the outset, in this book on cognitive development in humanoid robots. And so you could read it there. But I'm always very conscious that, of course, SOAR is a work in progress. It's not finished yet, but it is developed very, very significantly since the 80s and the early 90s. And I would be doing a tremendous disservice if I left it just with that summary, and I don't want to do that. And I just want to point out that this is the new version of the diagram which encapsulates the SOAR at the moment, and it's got semantic memory, it's got episodic memory. This is the memory of your autobiographical experiences. We'll see in a moment that John Laird refers to this as a trace. Procedural memory, and I cautioned yesterday about being aware that procedural can mean the rules which define the operation of the system, as well as the procedural knowledge associated with motor action. In SOAR, it means the former. And you've got learning for all of those memories as well. And here's the chunking that I mentioned, the learning a rule. And there's also reinforcement learning now in SOAR. It's got a symbolic working memory. So this is the reason I showed you that little taxonomy earlier on. So we now also got working memory here. And we've got a perceptual short-term memory, storing information that has come through the perception system. SOAR also has a visual memory, a long-term visual memory. It's not clear to me why necessarily it's separate from episodic memory. It's probably a representational issue. We'll see in a moment that in fact it uses a kind of a scene graph of the scene. So it's a way of symbolically decomposing the iconic information, the eidetic information that's in your image, in your perceptual system. Mental imagery, I mentioned yesterday a lot about this idea of internal simulation and prospection, and here we have it in SOAR as well, and perception and action. Now, this is a fairly shallow overview of SOAR as it is today. And I've never been particularly happy with just leaving it there and then moving on, even though that this is, I'm still in my progressive deepening approach, and I can get away with claiming that it's only a shallow abstract version of it. But I was really delighted when I came across this conference that Michael Bates organized with his team in the University of Bremen, where I work now. And they organized a conference in late December on the 30th called Democratize AI. And guess what? John Laird was one of a very distinguished group of speakers. and panelists for this conference. And he gave a talk on video, 1 hour long, on open research and the SOAR cognitive architecture. So I've taken the liberty of extracting a short excerpt from this so that you can hear SOAR described by the author and the developer of SOAR himself. So this will just take us about 6 minutes. Please let me know if the sound is...
Hi, this is John Laird, and I'm going to talk about the SOAR cognitive architecture today, and also how we have been doing open source research. This structure of the current version of SOAR, SOAR 9. This was an extension which did add some new memories and learning mechanisms. If you see, sort of central to the system is the symbolic working memory that holds the system's current goals, the current state of the world. It also, in order to feed into that, we have information coming in from perception, but an important component of that is the spatial visual system. This takes the vision in, but then creates a scene graph representation, which is both object-based but also spatially based, so that it has metric information, and from that we can extract relations such as on top of, next to the right of, that are then symbolic representations that the system can reason over. Having that kind of information in the working memory would be very expensive to match against, so that is a reason why we move this out to a spatial visual system. The reason we have different memories, the perceived memory is actually what controls the reasoning in the system. So it gives us context-dependent reasoning, but it also supports things like planning and meta-reasoning. We have semantic memory, which contains all the long-term factual knowledge that the system has, and then episodic memory, which is a continual trace of the system's reasoning over time. And associated with all these these memory systems, we have learning mechanisms. Finally, that we have action system that can go out to the world. I'm now going to go through a simple example that is not reflective of what the system can do for robotic applications, but it gives you an idea for a human as to some of the kinds of reasoning SOAR can do. So we're going to start out, and I'm going to just verbally ask you to do some reasoning, and then we'll go and sort of look at what that would be in SOAR. So I want you to imagine the word wow. Now I want you to flip it upside down, and then I want you to think of the last time you saw the spouse of that person. So that would be maybe the last time you saw your father, and maybe that's never, but maybe that's been very recent, or maybe it was a while ago if your father passed away. But the point is, you're using all these different components, and it was effortless, hopefully, for you, and it didn't seem like you were suddenly switching between them, but that's what we would model in terms of that. So if we go through how that would happen in SOAR, we get audio perception of imagining the word wow. We then have to go into semantic memory in order to translate that into symbol structures. And then once we have that, that's going to be used to access procedural knowledge. Actually will cause that to be imagined. So we have some skill about how to do imagination, and that then is imagined in the visual buffer. We then say rotate, and that's maybe nobody's ever asked you to rotate something in your visual memory before, but that would come in, go to symbol rotate, and then that would have to go into procedural knowledge as to how that would be performed, and then we would rotate that. And then this is where things get a little interesting, I think, is that we have this representation here that is a non-symbolic representation. These are the actual characters, and we have to parse it. So we originally parsed wow coming in through an audio channel and then making contact with our semantic information. Now we're parsing mom coming through an internal, I would claim, visual representation, and then we're going to make contact to the symbol mom, and that's some symbol, but then we say, look up say something about a spouse. That's going to have to go into semantic memory as to who's the spouse of mom. That would be your father. And then that would be something we then go and search in episodic memory for. When have we seen that person? And we might get some episode, here it's E555, that we then retrieve, and that has associated last Sunday, and so then we would say Sunday. So this is an idea of just how all these different memories and representations can be used in order to perform a task. So robotic platforms over the years, here's many of them up until about 5 years ago. They include mobile robots, they include hands, a lot of mobile robots. They also include underwater vehicles and also sort of some toy robots. We hooked SOAR up to Mindstorms for fun. And here is what we've done recently at Michigan in the last couple years. So we've hooked SOAR up to a bunch of different simulators, a homegrown simulator that we use to do a lot of different games. There's the April ARM simulator, which is developed by the April lab at Michigan, and lets us do hand, eye, and gripper type manipulation of blocks. We also have the April Magic Simulator, which lets us create indoor scenes and outdoor scenes as well. And here we have an agent that goes around and picks up objects and does what's called a patrol task. And this is hooked up to AI2 Thor, which lets us do reasoning in an indoor environment. But we've also done tabletop robots. This is a robot arm created by Edwin Olson's April lab that we've used to do a lot of different games. This is the Fetch robot, which also does the same thing. And then this is the Magic robot for outdoor, and we even hooked up SOAR to the little Cosmo robot. So one of the things that's really important to us is being able to hook up the architecture to lots of different environments and lots of different tasks. And the code, it turns out, that runs here is exactly the same code that runs here. The only difference is in what is the interface to the vision system and to the mobile robot controller.
Okay, so let's...
Hi, this is John.
Let's carry on.
And I'm going to talk.
Okay, so yeah, I'm grateful that I had that video clip. It's the first time I've used it, and I think that's a lovely introduction and an overview of the SOAR cognitive architecture. And it makes the point also that SOAR, which has been used for many, many different applications, also has been used in robotics. So let me move on now to another hybrid one. This is ACT-R. So this is John Anderson's candidate theory of cognition, or unified theory of cognition. It started in 1996. I think the principal paper was published in 2004. It's now in version 7. It also is a production system in the sense that it uses and fires rules, and it operates again in a cyclic operation. What's different about ACT-R in this case is that ACT-R is mapped onto different regions in the brain. So it's very much more a cognitive neuroscience version of a cognitive architecture. The difference between the production firing in ACT-R and in SOAR is that only one rule fires at a time in ACT-R, and then you take a decision based on that. And then each cycle takes approximately 50 milliseconds, say the amount of time that models effectively the speed of operation in the brain. So that's ACT-R. Again, there's a summary of that in the survey that I mentioned. I'll make available all of these overviews in these surveys if anyone is interested in them. It's my third one. Arian is one of my favorites. The way that it can explain the idea of hybrid. So Clarion is Ron Sun's cognitive architecture. Ron Sun works in Vanderbilt University, Rensselaer Polytechnic, and there are 4 subsystems in Clarion. There's an action-centered up here center, a non-action-centered subsystem, a motivational system with goals, and then a metacognitive subsystem over here. What's significant about Clarion is obviously all of the different subsystems interoperate, but they all have both symbolic and sub-symbolic representations. So it's got an implicit connectionist bottom level, and each has an explicit symbolic top level. And what's particularly interesting about Clarion is that it allows information to flow both ways. So you can have knowledge flowing from bottom up, from implicit to explicit, and also the other way around, so that you can encode in your implicit processes knowledge which had previously been explicit in your symbolic processing. And it's one of the few cognitive architectures that focuses on doing exactly that. Again, a summary of that is available in the Springer book. And now let's have a look at a symbolic one here. And I wasn't sure which one to choose. I was torn between choosing Icarus, and Glare is another archetypal symbolic cognitive architecture or connectionist one. But I chose Icarus because it's extremely well known. This is Pat Langley's cognitive architecture. And again, it's got, we can see here, it's got long-term memory. It's got both procedural memory, this skill memory in that case, and it's got its declarative memory, its conceptual memory. So with learning through skills and then learning how to do inferences. Yeah, I don't know if it's ever been used in robotics. The reason it's a symbolic cognitive architecture as opposed to a hybrid one is that it is almost entirely symbolic in its operations, despite the fact that some of the cognitive structures are modulated with numeric functions today. One might make an argument that because of this, it is a hybrid cognitive architecture, but it's an archetypal symbolic cognitive architecture. So that's Pat Langley's Icarus. Again, a longer description of this if you wish to read about it. And then over on the other side, we'll have a quick look at one emergent one. This is the BBD one, the brain-based device architecture. And this is Jeff Kretschmer's cognitive architecture, which he developed with Gerald Edelman. So this was developed in the era before the deep learning revolution. And it was based on taking neural networks, but not just one single neural networks. The idea was that it wanted to emulate the way that the brain is organized. So it simulated the nervous system in a kind of a coarse-grained way. So it was a collection of neural elements, if you will. So multiple neural networks within it and the way that they interacted in order to get you your cognitive behavior. So it differs from a strictly connectionist approach in that it's looking at the nervous system as a whole and the interaction between the different regions within their simulated brain. So that was the idea behind the design of the BBD one. And they experimented with it using mobile robots. So that's BBD. A longer description if you want to read more about that in the Springer book. And now this takes me to Isaac. So now I'm going to go down one more level in my progressive deepening hierarchy, and I'm going to focus on Isaac and spend a little bit of time explaining to you how it works. So this is Isaac. This is Kawamura's cognitive architecture. And it was developed for a humanoid robot, also called Isaac. And it is very definitely a hybrid cognitive architecture. It's also an agent-based system, and here I need to be careful when I say a software agent. I don't mean an agent in the cognitive sense. So agent is also often used as a synonym for either a human cognitive system or a robot cognitive system or an artificial cognitive system. But in this case, it's an agent-based system. So we have individual software processes running asynchronously and communicating with each other by message passing. For those of you who are familiar with ROS, exactly the same thing, or for those of you who are familiar with YARC. So it adheres to the component-based software engineering paradigm. So that's the way that it's implemented in terms of software. So we have these individual semi-autonomous agents, which are software agents working away and communicating with each other. Now, let me walk you through the various components, and then I'll explain how they interact with each other in order to accomplish a goal and in pursuing a task. So we've got perceptual agents, we've got activator agents, different agents for the arm, the head, and the hand. And then significantly, this first order response agent here, which provides you with a short circuit between your perception and your action. But it has a second role as well in interacting with working memory, which I'll speak about. It's got 3 memory systems, and you'll see now again, these are the memory systems we mentioned at the outset. I've got my short-term memory, we've got long-term memory, and we've got working memory. The short-term memory system is a way of representing the information which has been derived and produced by your perceptual agent. And it comprises 2 things, a sensory egosphere. So this is a kind of a geodesic dome or geodesic sphere, which can be indexed by angles and will therefore allow you to identify what's been perceived in some direction in an egocentric frame of reference for the robot. So all of the perceptual events then are mapped onto this sensory egosphere. And then you have your attentional network, which determines what perceptual events are the most relevant and which ones should then be transferred into working memory so that they can be used in the task that's being pursued. In long-term memory, we have the 3 classic types. We've got the semantic and episodic. These are the robot's declarative memory of the facts it knows, both the facts which are autobiographical based on experience and the facts, its knowledge about the world and its environment and its capabilities, and then it has procedural memory. And this procedural memory for Isaac is different from the procedural memory in the sense of SOAR because it represents the motions that it can perform. It's not the rules which govern the behavior of the product, governs the way information is processed. So episodic memory then includes your external situation, the goals, your emotions. This is the first time I think I've mentioned in cognitive architecture the importance of having an affective aspect in cognition. 20 years ago, people were not talking about affect in cognition or cognitive systems, but now you really can't talk about cognition without saying how the affective aspect of it modulates your reasoning or your rational behavior. So emotions are extremely important now in modeling cognition. So obviously it's also got memory of your actions, the outcomes that arose from those actions. So here we have episodic memory somehow representing the consequences of your experience, your actions in the world. And finally, some evaluation of the outcome. So how close if it was an action that you took to pursue a goal, how successful was it? And did you receive any rewards? So these are all stored in in Isaac's episodic memory. And the episodic memories are connected by links, which then give you extended behavior over time. So as you transition from one episode to another. And it's also hierarchical, so it's multi-layered. So it's quite sophisticated in terms of its organization of episodic memory. The working memory then temporarily stores whatever information is necessary for carrying out a task. You can think of it, if you like, as a form of cache memory for the short short-term memory. And the information that it stores, which are called chunks. So these are different chunks to the chunks we had in SOAR. And effectively, these encapsulate the expectations of future rewards. So these have been learned using a neural system. So we have in our working memory memories and then an expectation of what the value of that will be if I use that knowledge. Now, the next component over here is in a subsystem called the self-agent. And the self-agent has two subsystems, the control and reflection subsystem and the goals and motivation subsystem, and two agents in each one. In the cognitive control and reflection one, we have the central executive agent, or CEA, and here we have an internal rehearsal system. So the central executive agent determines the operation, if you will, of the cognitive architecture and how information and knowledge is moved around. And then the internal simulation rehearsal system does the internal simulation of simulating the outcome of a candidate action that it might be selecting in the pursuit of a goal. The goals and motivation subsystem over here then encapsulate the intentions of the agent, so that's where the goals come from. And crucially, those intentions are modulated by affect, by a computational version of emotion. So the CEA, as I said, is responsible for the cognitive control. It invokes skills in order to try and perform some task or achieve some goal using its attention and using past experiences. As I said, the goals are provided by the intention agent and the decision making is modulated by the affect. So that's the structure of Isaac. Let me now very briefly take you through the operation in a simple way of Isaac. So this is its behavior over time. So normally the first order response agent, which is always active, it produces reactive responses to sensory triggers. So this would be like a perception action associative process, and it's fast. And so it's very quick. So based on this, you can invoke an action based on some stimulus that appears in your perceptual agent. And that allows for a very quick reactive control. But it's also responsible for executing tasks. And so to do that, when you are assigned a task by a human being, you're given this task and you're given a goal by the human that's using Isaac, the FRA then retrieves that skill from procedural memory. So on the basis of prior learning. So it tries to find a skill that matches the task that it's being given. And then it transfers that into working memory, along with whatever information is available from the short-term memory, from its perceptual system. So that gives you its context, this gives you the skill, and then that allows the that knowledge, then that skill to be transferred over to the activator agents, which are then responsible for that particular behavior. And it's suspended whenever you get a react or whenever a reactive response is required. So this loop will preempt the execution of that if necessary. So that's the way that Isaac works. So, so this is effectively, again, like an associative approach. So you have a skill, you associate a skill with a goal or a task, you associate a skill with that, and then you execute it. Now, what happens if you can't find a skill which matches the task? In that case, the central executive agent takes over. And it then goes to its episodic memory, its past experiences, and it looks for situations where that task was executed in the past or where there were similar goals in the past. And on the basis of that, it finds that in episodic memory, and it selects a behavior percept pair because it's got knowledge about what the current context is here. It retrieves its episodic memory, and then it uses its internal rehearsal system to simulate the candidate action or the candidate skill, and to see what the outcome would be. And if that outcome then matches the goal of the action, which has been requested by the user, it'll be executed. It's executed by transferring it to working memory and then onward to the activator agents. And that's how you get cognitive control. Let me just preempt something I'm going to talk about tomorrow a little bit. Here we have, I gave you 3 modes of operation here. We have the first order response, which is effectively a stimulus response, fast reactive approach. We have a similar reactive approach here, which is kind of a fast way of working where you recall knowledge from your episodic memory because it matches a previous skill. So, and then you use that skill to carry out your action. So this is like system 1 in thinking fast and slow, Kahneman's idea of a 2-system approach to cognition. And the CEA over here with the internal system is the slow approach, that's system 2. So in a sense, Isaac is an instantiation of the system 1, system 2, the dual process approach model of cognitive systems, made famous in Kahneman's book, Thinking Fast and Slow. Okay, so that takes me to the end of my short tour of cognitive architectures. I'll pause and see if there are any questions from anyone wants to ask a question. You're free to ask questions at any time you want and stop me. Please do.
So if anyone has a question, you can please use the raise hand option in the participants tab, or you can post it directly in the chat and I will read it out in case you're shy.
I'm reading the chat as I'm here. Are my slides coming through in a blurry manner, Anna?
So sometimes the connection, I think, drops on your side. However, I shared the link to the slides from your website so people can have them in parallel, especially for the slides that had a lot of tiny text. So it may be easier for them to switch. It's nothing. Okay, so we have Levi. Okay. We don't hear you though. I mean, you're unmuted, but...
Hi, can you hear me now?
Yes, perfect.
Thank you. Okay, thank you. So my question was about representation. So it was mentioned quickly that we're using neural networks to generate representations for things, but neural networks generate very different representations depending on the network we use, and all these different parts need to talk to each other. Are we going to talk about how that representation is done at some point, or is there anywhere we can look for that?
Yeah, great question. And here I have an admission, or perhaps even better, a confession. In these talks, we're working at a conceptual level. So while I said cognitive architectures have to make commitments to representational formalisms, I'm not going to get down to that level of abstraction in any of the cognitive architectures that I'm talking about. I'll mention a little bit when I talk about CRAM tomorrow, but just a small amount when I talk about the logics that CRAM uses. But the question that you ask is an entirely valid one, and that's where you have to go to the literature and look at the individual descriptions in the papers. And in my experience is that they're very often lacking in the level of detail. So most cognitive architecture papers tend not to drill down into the gory details of exactly what representations they're using quite often, which is problematic, I think. That's not true universally, but it's true for many of them. They work more at a higher level of abstraction. The issue that you mentioned, though, is the interoperability between different types of representations within a cognitive architecture. And I think that's a very live topic, because you need multiple types of learning, both sub-symbolic and symbolic, and then how do they interact? If you want to understand how the symbolic and the sub-symbolic interact in terms of how neural information, connectionist information is made available to a symbolic subsystem, the best place to go to begin with would be the Clarion cognitive architecture, because Ron Sun does an extremely good job in the way that he builds this bridge between the two of them and makes it very explicit how implicit knowledge in a connectionist network can be made explicit in rules. and vice versa. I don't know if I've helped. It's not a very satisfactory answer, Levi.
That helps very much. Thank you.
Welcome. Carlo.
There's Carlo, yes. Carlo, you should accept the...
Okay.
There we go. Okay.
Okay, can you hear me?
Yes.
Excellent.
Yes. I wanted to ask you if you can define better the sensory memory with respect to the mere perception and to the working memory. For instance, in iSac, you show the egosphere, the sensory egosphere. Yes, just this. If you can define better this aspect. Oh, sorry, this aspect of sensory memory.
It depends. Well, in iSac, I'd have to go back and I'd have to look at the exact the details in the paper. The details are in there. My recollection of this is that this is still represented in an iconic subsymbolic manner. But in working memory, it's been encapsulated in some symbolic form so that it can be subject to some form of reasoning. The exact process then is going to be specific to iSac. We saw it in SOAR as well when John Laird mentioned his visual, where is it? Yeah, the long-term visual memory. Remember, he referred to that as being a scene graph. So scene graph is effectively a labeled image, both with spatial and semantic tags saying what it is, what it's used for, and where it is. So that's how SOAR implements that representation. I can't remember the details of how it's done in iSac. But if you want, send me an email and I'll send you the paper to say you're looking for it. Anyone
Okay,
else?
thank you.
Here I'm going to kind of have I'm not very happy with the fact that I haven't been able to answer Carlo's question in a particularly deep and satisfactory sense. And let me just remark as an excuse to excuse myself is that working memory has a very limited capacity. And so the link between my long-term memory of having studied SOAR and working memory, so I don't have it available in my working memory at the moment, and my recall isn't as good as it should be. So that's my explanation of why I haven't been able to. But when I teach, I get the questions like that, and I always come back in the next class. If we have another one, I'll have to do some homework tonight, and I'll come back, Carlo, tomorrow, and I'll have a better answer for you.
But you also very kindly shared all of the resources with us, so everyone who is interested to dig in a bit deeper can very easily find all of the references that you're mentioning.
Yeah.
Okay. I think we can continue maybe with the second half because I don't see any other raised hands, and then we will do the second round of questions.
Super. Okay, super. Great. All right, so now let me move on to what's known as the Common Model of Cognition, or also known as the Standard Model of Mind. I'm only going to introduce it to you here. If you find this to be extraordinarily useful and helpful, I have a much longer talk than the overview that I'm going to give you here. But we'll see. So if we have time, I can go to that other talk and I can walk you through it. I pulled it out just before we started today, so it would be easy to do. And though I haven't revised it, I can probably walk you through it fairly easily. So the Standard Model of Mind. So this is the result of some recent work that's been done. It was published in AI Magazine in 2017 by John Laird, Christian Lebier, and Paul Rosenblum. And there's a précis of it published at roughly around the same time, and there's been some subsequent work. And there's a community behind this as well. So you can subscribe to the mailing list for the Common Model of Cognition, or the Standard Model of Mind. So this is the original article. And so if you find this interesting, it's really worth reading that particular paper. There's a lot in it. So here is the SOAR cognitive architecture that we talked about at the beginning, but this time color-coded. And the color-coding represents a different type of memory and module in the Common Model of Cognition. Here we have procedural memory. Here we've got declarative memory, working memory. Green for your motor skills and your motor subsystem, and then yellow for your perception. Gray is, I don't think, used in all of them. So that's the visual buffer in SOAR. In ACT-R, color-coded again, we have our working memory, our procedural memory, our vision, and our declarative memory over here. So again, color-coding it. And color-coding Sigma. This is Paul Rosenblum's recent cognitive architecture. And Paul Rosenblum obviously had some heavy influence in the development of SOAR early on. And so what's the point of all this color-coding? The idea is that there was a feeling in the community that, there were so many cognitive architectures. They wanted to find a way of seeing, could they have some form of consolidation, some form of standard model that meant that we could have a way of talking to each other in the community and making progress as a community. It switched to the Common Model of Mind then in 2018 at the AAAI Fall Symposium. So the community, while the original article referred to a standard model, the community felt that maybe a Common Model of Cognition was a better banner under which to have this discussion. And so the idea was to have a kind of a consensus and to look at cognitive architectures from AI, SOAR and Sigma, from cognitive science, ACT-R, Clarion, and LIDA. LIDA is Stan Franklin's cognitive architecture. Cognitive architectures in the neuroscience field, which I've said very little about, in fact, nothing. SPAWN, which is Chrysalis Smith's cognitive architecture. Labra is another neuroscience architecture. Randall O'Reilly's one. And then we've got cognitive architectures from the robotics domain. This is Albus's one for the RCS, and then Matthias Schweitz's DIARC cognitive architecture. So they looked at all of these and they said, okay, what's common to these? And this should remind you of the unified theory of cognition, because unified theory of cognition in Newell's sense is trying to look at intelligence and cognition from all perspectives. So they took this very seriously and said, we want to have input from robotics, AI, cognitive science, and neuroscience. And then they came up with this idea of this prototypical, very simple diagram to show that a cognitive architecture is going to have perception, it's going to have action, it's going to have declarative long-term memory, it's going to have procedural long-term memory, and it's going to have working memory. And we've seen that in all of the cognitive architectures in the different guises. And it's particularly evident, obviously, in the current version of SOAR, and it's particularly evident in Isaac as well, as we've seen. So the idea derived from particle physics, where they have a standard model of understanding their current, everyone's accepted model of particle physics, and they wanted the same thing for human minds. So it was an effort to try and combine what's known, a kind of a reference point about cognitive architectures, with the focus on trying to extend or revise it. So by explicitly putting everyone on the same page with this common model, then we can decide what needs to be developed and what needs to be extended and what needs to be gotten rid of in order to move the field forward. It's not intended to be a complete theory of cognition. It's not intended to be a complete model either. And it's certainly not intended to be an implementation. In other words, it's not a cognitive architecture either, because don't forget, a cognitive architecture is effectively a hypothesis of how cognitive behavior is accomplished in humans, in animals, and in machines. So it's not that, it's rather the reference for that to say what a cognitive architecture would need. So in a sense, it's a little bit like what we sometimes refer to as a cognitive architecture schema. there are many omissions in the paper, and they're intentional. And those omissions are effectively an implicit statement that there is no consensus yet, and that a consensus is needed on these issues. And so, but the one thing about which there is a consensus, and they take this as their axiomatic basis for the common model of cognition, and that is that a cognitive architecture provides the appropriate computational abstraction for defining a standard model and effectively for defining cognition itself. So, but the model itself is not a cognitive architecture. But what it's saying is that you have to have a cognitive architecture if you want a model of cognition, in the sense that a cognitive architecture is the model of cognition at an appropriate level of abstraction. The idea is that you would be able to evaluate single components within that standard model, evaluate different combinations of components, the way working memory interoperates with, say, with procedural memory or episodic memory. Ideally, those components would be openly available for everyone in the community, and therefore you would be able, for the first time, to be able to have cross-platform benchmarking and facilitate some kind of testing, which was one of the ways that the machine learning field in the last 20 years made huge strides, when you couldn't get anything published in the machine learning field without benchmarking against standard data sets. So, and I remember years ago at a meeting in Robotics it was in Graz, I think, being the community, the cognitive systems community at the time was upbraided by somebody who said that we as a community need to embrace that benchmarking ethos a lot better than we do. Who was it said it? It was Bill Triggs. Bill Triggs got up, I remember, and he stood up and he said, everyone in the community needs to realize that it won't progress as a discipline until this idea of having standard test beds and benchmarking of your capabilities in the same way that the machine learning field did. And he's right, but that doesn't make it easy. But I think it's a point worth bearing in mind. So some key aspects about the standard model of mind, or the common model of cognition. It focuses on structure and processing, memory, learning, perception, all the things I've talked about, but very little on action. So in terms of the motor system, it makes the assumption that it can convert the motor commands and it converts symbol structures and metadata into external action, and that they control the body effectors. And that's, with due respect, that's almost it. So there is no consensus on the form that should take in the standard model. And it's curious, it's also a little bit depressing that is the case, because if you listen to, for example, Daniel Wolpert's famous TED talk on the real reason for brains, it's all about action. And so cognition, cognitive systems subserve your need to act in the world. And so it's a little bit unfortunate or sad that we don't yet have a consensus on perhaps one of the most important aspects of cognition. So it's very, very important, and the relationship of all of this to cognition. So I don't think you can just wave it away quite so easily as it is done. And I don't think John Laird and Christian and Paul are waving it away at all. They're just saying we don't have a consensus, and therefore they're saying we need more work on this. And so putting motor back center stage in exactly the way that Daniel Wolpert does, I think, is going to be pivotal moving forward. So this is a quotation here, we'll get inverted commas. So the standard model remains incomplete and is silent, for example, regarding, and here we have metacognition, emotion, mental imagery, internal simulation, direct communication and learning across modules, so cross-module interaction and modulation. And even the distinction between semantic and episodic memory, they're silent on whether or not that's a valid distinction to make. I mean, they're clearly agreed that the semantic and episodic memory together comprise your declarative memory, but whether there's a useful distinction to be made. But it cuts across a lot of the work that's been done over the last 15 years in cognitive science, where episodic memory and semantic memory have, well, it was Tolman who introduced the distinction and gave the semantic memory its name. But it's still very, very important as to distinguishing the autobiographical memory, the constructive nature of that, and the way that it impacts on your what's called episodic future thinking, and the way that episodic memory allows you to simulate and pre-experience your future as you internally emulate or simulate what would it be like to carry that action out. And you don't need semantic information necessarily to guide that. So the distinction between semantic memory and episodic memory seems to be there, at least on that basis. You will also acquire knowledge, third-hand knowledge. So we learn from books, we learn from the internet, we learn from listening to people, and that information isn't part of your experience. Of course, you have to experience it to learn it, but it's not a part of your personal experience. And that knowledge here is clearly semantic, and it's been very often communicated through a linguistic channel. Also, in semantic memory, you can form quite rich networks or of relationships between your semantic entities. Whereas episodic memory, we know, is more restricted to spatial and temporal ordering. And mechanisms for social cognition, silent on this as well. And I mean, Lev Vygotsky would be turning in his grave, obviously, because social cognition is so important in terms of A, how we learn, B, how we experience the world, and also it's part of why we are conditioned. We are human beings, are social animals, and so cognition subserves that interaction as well. And cognition is essential for forming theory of mind or perspective taking or understanding the goals and intentions, aims, aspirations of the agents with which you're interacting. So there's a lot yet to be done in the standard model of mind or the common model of cognition. As I said, this is a short, brief overview of the common model of cognition. There's a lot more in the paper, and I have another presentation I gave last summer on it, which runs to approximately 70 slides or so. So that gives you an indication of the fact that I have subsampled very coarsely in this overview here. For reading more, yeah, all of these resources I can make available to anyone who wants them. If you can't get them either on my website or on my wiki, or just by searching the net. Which brings me to the end, apart from one thing. I mentioned Daniel Wolpert's TED Talk. This is a great video, really worth watching. And if you want to see the full exposition of SOAR by John Laird, it's available here as well. And as Anna mentioned, of course, this talk is available on my website, Module 6, Lecture 2.
Yes, and also the slides will be available to all participants as well, so they can...
Sure.
Sorry, I interrupted the last slide.
No, that's my safety net. I'd forgotten about it.
Okay, there is
just in case I get tough questions. I have some backup. Yeah.
Wonderful.
Yes.
So we have as first questioner Alessandra. Let's see if it will merit the Shrek.
Hi, Alessandra. It was, as usual, very, very interesting talk. I just wanted to ask you a bit more about these latest points that you raised on the fact that the standard model is silent on both the aspects of metacognition, emotion, and the mechanisms for social cognition in general. Yeah. And I was wondering, is it because some of the models of the cognitive architecture that have been proposed exclude the importance of these components? Or it is because they put it in different places? So in Isaac, for instance, you were talking about the presence and the importance of emotion at the level of the episodic memory, for instance, or in the affect agent. Yeah. But when you were talking yesterday about the core cognitive abilities, I mean, there was not any point related directly or explicitly to either social cognition or emotion per se. So where would it fit according to you, or according to a general view, this element?
Well, I think it's simply been neglected, which is hard to understand in a way, because I know it's only in the last 20 years where it's become center stage, but it's inconceivable now that anyone would consider developing a model of cognition which didn't factor in affective states, because we know that your affective state modulates your behavior in very, very real ways. And in fact, there's an argument that, in fact, we don't even act rationally. We act irrationally, and we post hoc justify our rational actions. But of course, that's not the perspective that has been taken in the cognitivist tradition throughout the last 30, 40 years, which has been entirely a rational approach. And going back to the work by Herb Simon and Alan Newell, they had this paper, their Turing Award lecture in 1976, which, if anyone hasn't read it, I mean, it should be essential reading for everyone, whoever studies anything to do with AI, because it really was groundbreaking in what it has foreseen as being necessary. But they didn't mention it either, but they introduced this concept of a physical symbol system, and that is their model of artificial intelligence. And if you're an AI system, you're a physical symbol system, and that means that you manipulate symbols in order to achieve goals, and the point of intelligence is to avoid a computational explosion. And so you do that by exercising your intelligence as you're searching for a solution to a problem. But I think it's just been missing, and it's curious why. But even back in 2004, people like Murray Shanahan, when in his cognitive architecture, which was based on global workspace theory, he specifically had the amygdala as part of his model, which was modeling the action selection, which he called the basal ganglia in his architecture. But it explicitly had an affective modulation of your action selection process. It's just a fact of the way that it works in SOA cognitive architecture. It has to be there. It's there in SOAR. It's not there in SOAR. It is there in Isaac. It's there in Murray's one, and a few others. So it's simply that it has to be a modulating aspect. There's another aspect we talked yesterday about it in the embodied thing. It's another thing that's been omitted in a way. If you subscribe in any sense to embodied cognition, and where would you put that? But there are yet other things which are missing. There's a lovely paper by Mog Stapleton called, and she refers to what she calls being properly embodied. And by that she means not only do you have to consider your neural substrate and your physical substrate, but you also have to consider your hormonal system in a cognitive architecture. So if you don't do that, then you aren't modeling the whole thing, because we know, for example, that your hormonal system also modulates your decision making and your behavior, and the hormonal system and the neural system interact in the hypothalamus, and so it's a big system. And of course, you won't hear that in some cognitive architectures. Tomorrow, you won't hear any of this when I talk about CRAMP, because it's taking a different stance on what it wants to achieve. It has a very specific goal. It wants to do cognition-enabled manipulation in everyday environments. But it isn't interested in being a unified theory, as far as I know, a unified theory of cognition, but it is a model of how people work. It'll be interesting to see what happens and how it'll have to be extended as soon as the CRAM cognitive architecture has to start interacting with people, or the robots that it's controlling has to start interacting with people as they interoperate with the robot, or as they work or collaborate with the robot, because it will have to take perspectives. It will have to have a model of mind, and all of a sudden affective states, at least in terms of the other agent, are going to have to appear in the picture. And that if you adopt the mirroring approach in terms of how you think cognition happens, then of course you need the counterpart computational apparatus in your own cognitive system. So the answer to your question, Alessandra, is if it's not there, it should be there. And it's obviously a modulating component for your action selection and your action execution. Does that help?
Yes, it does. And now I'm super curious to go and scroll between among the different cognitive architectures. Which one have really addressed that explicitly, and where to know which kind of position was taken about that?
I must go back to that landmark, the survey, and see what they've got to say about that. I didn't pick up a great deal, but I don't want to prejudge it. I go back and look at it. Antonio, and then Levi.
Yeah. Also, just as a minor note to your previous reply, it's interesting to see how you're mentioning as separate components hormones and affect or emotions as making part of the decision-making process. Because I've also had experience with the work of Lola Cañamera and her group, where they're actually using them interchangeably in their motivational system. So the work of Cañamero and Antoine Hill works also exactly with this, of using hormones to provide an affective input, essentially, to the motivational system. It's a very interesting work. Alessandra, you still have your hand raised? Sorry, my bad, I was muted. Okay, so Levi, go ahead, and then it's Antonia.
Hi, I think so. I'm back with another somewhat related question. So if we were to, implement one of these systems, we would, at some point we would need a computer, and the computer would do something. But what we've talked about is very high level. How low level do you think we can start to specify these architectures and have them still make sense? If you have a high-level language, you have a compiler to do it for you, but for a cognitive architecture, we don't have something like that. So what are your thoughts on that?
My thoughts are that again, I'm doing progressive deepening here, but I haven't gotten down to those levels of details, but you have to. Mm-hmm. If you're being faithful to the endeavor, you have to get down to it, and you have to say how your what logic you're going to choose for your inference system, whether you're going to use a knowledge-based approach, whether you're going to use first-order logic, whether you're going to use a graphical model, what form of graphical model, whether you're going to use some kind of Bayesian approach, whether or not you're going to do your modulation through some symbolic inferential system, or whether you want to do it in another way with some network. But you have to identify those details. So for me, for everyone, for Ron Sun, it's not an architecture until you specify that, until you commit yourself to those low-level details. So cognitive architectures transcend multiple levels of abstraction. But the problem is that in the description of them in the literature, those details are very often skimmed over. But the devil is in the detail, and we need to know it so that we can replicate it and so that we can compare different approaches. So I think it's crucial that that's the case. With CRAM, I won't have a lot of time to spend tomorrow to talk about how it does that, but I will refer to specific computational details. So again, because I'm going deeper there. If I was to give an entire, I would need actually a couple of hours to give a decent overview of SOAR. I only gave you a schematic overview. But there are details in, not SOAR, I beg your pardon, in Isaac. If you look at the Isaac paper, there are details in there.
Great, thank you.
So,
thank you.
Yeah, so it's crucial. In the same way that my answer to Alessandro, it needs to be there, and also to you, Levi, these computational details and commitments to representational formalisms and processes have to be there if you have a legitimate architecture. Without it, you just have a boxology, yeah, a nice diagram and a good story, and that's not science.
Great, thank you. That puts me in perspective. Thank you.
Yeah. So
Antonio, go ahead.
Okay, so thank you, David, for the interesting talk. I have a question about the missing parts in the common model of cognition, because that one was mainly driven by the three cognitive-based architectures that you mentioned, so Sigma, Actar, and SOAR. And I was in the group. I mean, there were 4 different kind of groups within the 2 AAAI symposia that followed the paper, and every and each of this group was trying to address somehow some of the points that were raised also by Alessandra, for example, emotion module or metacognition, and so on and so forth. The point was that, so as you mentioned, there was not, given the kind of cognitive architecture that we were taking into account, a consensus. So the silence was driven by the fact that differently from the other kinds of short-term memory, long-term memory, and so on and so forth, there was not a unique, let's say, way to specify these aspects in all these different cognitive architectures. So there are emotional and affect-based agents developed, for example, in Actar or in SOAR. There are metacognitive elements developed in these architectures, but this aspect is left, let's say, to the model that is developed, to the individual model that is developed within these different kinds of cognitive architecture. So it was not sufficient to provide any kind of statement about let's say, any standard, let's say. So my question is, what are the, in your opinion, the cognitive architectures that should be taken into account in order to, let's say, improve the schema of the common model for what concerns the motor aspects, but also the mental imagery aspects, and let's say all the part that is currently missing, but that is probably missing because there was a bias towards certain kinds of cognitivist architectures.
Yeah, it's thank you for putting me on the spot in a way. I was at the AAAI meeting. I don't know if it was the same one, but I did listen to, Pat Langley was there, and I listened to a talk by John Laird at it, and I remember thinking at the time, I can't leave because these are very important people. But I did tire of the cognitivist overtones, and they weren't even overtones. I mean, you use the word bias, and I think that's true. I've been trying. I need to make something clear here, and I probably should have said at the outset. In giving these talks yesterday, today, and tomorrow, I'm trying to give a bias-free overview of everything, and in the same way that when I wrote the 2014 book, the primer, I tried not to allow my own convictions to intrude on what I was saying. I was trying to give an overview which was unbiased, and I'm still trying to do that, but you're not allowing me to. You're saying, okay, well, name the ones that you would use. I think it's an interesting question. I don't think I have a ready answer for you. I cannot give you a catalog of the cognitive architectures that would need that, but I know the literature I would start reading. I would certainly start reading the literature in the inactive systems community for a start. I would read more of the work that Mog Stapleton has published. The word wouldn't come to me earlier on when I was talking about the hormonal system. I should have said the endocrine system. So we've got our central nervous system with the endocrine system. And one caters for the autonomic operation of your system and the other caters for the cerebral and peripheral nervous system. And together they make the whole cognitive system work if you subscribe to that particular paradigm of embodied cognition. And I only know of one cognitive architecture which I'll have to look up at Lola Kanamera's stuff, but there was one I did come across which specifically had an endocrinal-based cognitive architecture. So I think it would be an excellent exercise to answer your question, Antonio, offline, and go through all of the 84, for example, that are in the survey, and identify the ones which tick that particular box. So in a sense, to augment the survey with additional cognitive abilities, I would include prospection in it, affect or emotion, depending. Some people don't like the word emotion, they prefer affect. So but it doesn't matter, it's the same thing. And then the embodied aspect would be something else that you might have to put in there at the meta level. And then to go through those 84 and see which of them actually treat this in any deep way, as opposed to making lip service. But I in terms of affect, the two I always zone in on are the ones I've mentioned, which are Isaac, because it's explicit in it, and also the Murray Shanahan's global workspace theory one. And LIDA might have it as well, because LIDA is based on global workspace theory. This is Stan Franklin's cognitive architecture, but I'd have to look it up to see. Okay, thank you. Yeah, but I think it'd be a great exercise, Antonio. Forget about writing a paper. It would probably be an essential prerequisite for moving forward with the iCog project. Yeah. Speaking, Giulio.
Yes, I mean it's sort of a borderline between a practical question and a more theoretical one. I mean, we are working with robots, so we basically are looking for real-time systems. On one side. On the other side, I mean, from your presentation today and yesterday, it is clear that a key component of the architecture is memory in different flavors. And regarding memory, I mean, the technology that we are using now to simulate or to implement memory in our system is still very far from the kind of association process that the biological brain does. So it's a sort of, it is more a serial search more than an association what you have to do. So in that sense, it introduces a sort of unsurmountable limitation in terms of how fast you can access or you can retrieve, or you can associate what you see with what you saw in the past. So I wonder, if we shouldn't try to implement a sort of slow motion cognition in order to get rid of the intrinsic delays that we have in the hardware we are using, or you see a possibility of implementing this kind of association that is the process that the memory is using in such a way that the system can actually work in real time.
Okay, so there are really two things here. There's the real-time aspect, and then there's the association-based retrieval. And I really think that they're kind of orthogonal to one another in the sense that the memory that we conceive, certainly in terms of symbolic cognitive architectures, we view memory as indexable. So you index memory and you retrieve on the basis of that, and you use pointers in order to speed that up, and you can have different levels of interaction, but ultimately you're using some form of a classic computer science index system. You know what you want where it's stored. But of course, we can also have content addressable memory, and that is exactly what you would want. And that's how certainly some aspects of the brain works through association. And yet those techniques aren't deployed as much as perhaps they should be. And I think that they should, associative processing, either hetero or auto-associative processing, needs to feature more strongly in architectures at some level of implementation. And it's interesting that Murray Shanahan's won the global workspace theory. He implemented it with effectively associative memories. He called them generalized random access memories, but effectively it was an associative memory system.
Okay.
And that opens up a lot of different possible types of processing, and perhaps opens up different paradigms of analogical reasoning as well, which I know you can do symbolically, but to do it in a different way might bring different yield different advantages. The time-based thing is it's curious that biological systems are slow anyway, and yet we measure access times in RAM in nanoseconds. So I think the speed is that of course we've sequentialized it in our computer model, and that's a problem.
Yeah, because I mean the brain is slow, but it is fast in some crucial aspects. Like retrieving from memory, from a big memory. I mean, you see a face of a person you haven't seen for years, and in less than 100 milliseconds, you remember who it is, and so on. Which is,
and yet you can't remember the word endocrine, even though you can see it.
Yes.
But you can't articulate it, but it's there. So
yeah.
My joke as I get older is I tell people there's nothing wrong with my memory. It's my recall is the problem.
That's exactly okay.
But of course, I mean, there's a lot of architectural issues associated with this which pop up because of the highly reticulated nature of the architecture in the brain, and you've got these long-range reticulations as well, links, and and they're bidirectional. So you've got links back down as well as moving forward. So there are organizational issues here in terms of memory which are extremely important.
Yeah.
But Julia, I remember I asked Luciano one time, Luciano Fadiga, when we were working together, I said, can you explain to me how memory works? He looked at me, laughed, and walked away.
Yeah. No, I mean, it is a crucial aspect, and I wonder, if given the fact that we cannot speed up memory, maybe we should slow down actions in our robot to test.
And act but the beautiful thing is, we can do this with simulators if we want to.
Sure. Yeah.
And that's fine.
Yeah.
But I think I wouldn't give up on the ability to work in real time too. Over the summer, I spent a very, very enjoyable 3 months actually working in the Center for Interdisciplinary Research. You're a member of the Cobham group in the ZIF there, and they've been working on the situation model framework, which allows, it takes on board the dual process approach, the Kahneman's System 1 and System 2, for allowing you to have, how shall I put it, I think Michael put it one time as kind of pre-compiled knowledge ready and available in the way that you have in your long-term memory, and it can be retrieved associatively or through some form of index system if you want, and that it is immediately available for working. And you don't necessarily have to go through the slow process. So I think taking the situation model framework, I think as a blueprint for at least a part of a cognitive architecture, I think would be an extremely profitable thing to do.
Yeah.
And there's a lot in there. It really bears a lot of studying. I enjoyed reading their papers very much. So this is work that was done, for those of you who don't know, with Helge Ritter and Werner Schneider and Bielefeld, together with Josefina Albert and Xiaoxia Xuan, doctoral students.
Thanks. No, we should not. We should stay with real time. I mean, I was not suggesting to. Yeah.
But I agree. I mean, the other thing, Julia, if you'll forgive me, I have to, because you introduced the word time.
Yeah. But
I think the other issue is that we have to remember that cognition is a temporal process. It's a dynamical process, and the computational paradigm sometimes condenses this, and it makes time atomic. And of course, you lose a lot when you lose the dynamical aspect of it. But people have been saying this, like Esther Telemann and Helen Smith, for years, that we should be viewing cognition as a dynamical process, not as a purely computational.
Yes.
I can't remember who advocated a few years ago the idea of someone advocated dynamical computationalism. Was it Crutchfield? Could be. So the dynamical aspect has to be addressed.
Yeah, thanks. Thank you.
We have a question from Yanis, and then it's Levi.
Okay. David, there is a cornucopia of cognitive architectures, as you showed us. And it seems that people, individual researchers, put their individual biases into the problem. So my question has to do with the notion of a minimalist cognitive architecture. What are the minimal requirements that you must have? What components you should put together? Because, you know, there is no end. You can put emotion, you can put this, you can put that, and you can put language, you know, and so on. But the question is, what are the minimal requirements? I don't even know if this can be answered for having a functional cognitive architecture.
This is a conversation that Giulio and I have had for years, and we've come at this from many different directions, and I've never come up with a satisfactory answer. So now, Yanis, you've asked me, I'm going to make an attempt to answer it, which I don't think I would have. I know for sure I wouldn't have answered this way 6 months ago. But over the last 6 months, I've been exposed to some very, very deep thinking, first of all in Bielefeld, working in the Cobham group, in the ZIF, and also over the last 3 months working in Bremen, understanding what was underpinning CRAM. And I'll try and convey this tomorrow. And not just learning Lisp and being able to write CRAM plan languages and explain to students how to do that, but to actually understand what was the theoretical underpinning of it in the first place. So my simple answer to you is you're going to have to develop as a minimal, let's call it a component, or let's call it an element. I'm not sure I like the word components because it's too reductionist and doesn't leave enough latitude for different types of implementation. So the core element is you're going to have to have a generative model in your system. The reason I say that is that the generative model is a way of formally modeling a distribution between the effects of your actions in the world, and then being able to, if you have a probabilistic model, then being able to sample that and then be able to infer what you should do in order to bring that effect out. And so this goes back, and the reason I say this is because it goes back to Daniel Wolpert's work, who's mainly working in motor cognition. But he's got a wonderful, wonderful paper he published with Paul McNamee about 2 years ago, where he begins with this idea that trying to understand how you should act in the world, and it all comes down to building internal models. So the generative model is the way, it is the device that you need in order to predict the outcome of your actions, rather than just being a kind of a Brandenburg vehicle reaction system. That's not a cognitive system. So a cognitive system will be able to predict the outcomes of what it's doing, right? So that's, I take that as axiomatic. And the generative model is the mechanism. So you have to have that to begin with. So therefore you have to have internal models. The second reason I'm more confident in saying this now is that when I was in Bielefeld, one of our exercises I was given was to write a presentation to summarize I think a wonderful paper written by Anil Seth in 2016, where he takes the work of Carl Friston and others on the free energy principle. But he wrote a paper called the Bayesian cybernetic brain. So he had this way of combining cybernetics and probabilistic models as well as the free energy principle. But the point is, in cybernetics, they have this thing called the good regulator theorem. The good regulator theorem says that your system, any controller of a system, must be capable of having as many states as the system itself. Or to put another way, you cannot have a simple controller of a complex system. Or put another way, if you want to control complex systems, you need models. They have to build models. They have to build internal models. And the generative model is quintessentially the kind of internal model. From that, you can have inverse models and forward models. And you can learn how to sample them to make inferences about how to act. So that's my attempt at an answer to a question that you asked that I couldn't have answered 6 months ago. And I may not be right, but at least that my experience of the last 6 months in Bielefeld and Bremen has colored me sufficiently that I think that I can make a strong case for that. I don't know if you're happy with that answer.
It's good. Basically, underlying your answer is the notion that the action system is the fundamental one in a cognitive system.
Yep.
You should be able to generate them, predict them, recognize them, put them together, compose them, and so on.
Yeah. And then there's a second dimension, and I would have to say, because I think cognition is only the surface layer of what is a bigger topic, and that's autonomy. So cognition is a means to an end, if you will, and your ability to maintain yourself to do what Bickard refers to as recursive self-maintenance. That there are processes at work there, and cognition is a part of that. So you need to factor that in. So if you admit that cognition is merely a facet through which you view the process of an autonomous system or autonomous systems theory, which is the view that Humberto Maturana and Francisco Varela took, for example. I mean, they were interested in cognition, but actually it was autonomous systems theory that Varela was most famous for. And so but again, it's about, I mean, if you think about cybernetics, cybernetics means steermanship. It's a governing system for looking after the system as it maintains its integrity in a world around it, building models of that world in order to accomplish goals, if you want, from a behavioral aspect, but ultimately it's about maintaining its own integrity. And but that's about action. And I'm not going to spoil it for people who haven't watched Daniel Wolpert's TED Talk, but his opening 2 minutes has a wonderful, wonderful example about how dispensable brains are as soon as you stop acting. For those of you who haven't seen it, go watch.
Good.
Thank you. Okay, Levi, can go ahead.
Yeah. Thank you. So you started talking about cognition as a dynamical system, which answered my question I initially raised my hand for. But that leads to another question. If cognition is to be thought of as a dynamical system, and we're going to put it in a dynamical world, are there any constraints that imposes on the cognitive systems? For instance, from a low-level linear systems theory, I could take two fully looking normal state space models, hook them in a loop, and get an ill-posed system that doesn't do anything that makes any sense. So that is my question.
So what was the question? Does it impose constraints?
Posing cognition as a dynamical model and then putting in a dynamical world, does the dynamical world impose constraints on these cognitive systems?
Yeah, I'm certain it does. Do I know what they are? No. But yes, absolutely. And that reminds me of something that Yanis raised in earlier on about the constraints that are also imposed by your ecological niche in which you work, your environment. When I used to teach cognitive systems, I always reminded students there's no such thing as a generic cognitive system. Right? There just isn't. I mean, there are cognitive systems or entities in an ecological niche, and they've evolved in that way. There will be principles underlying it, of course, and that's what we seek. What are those principles? But now we're talking about process. We're not talking about components, and that switch is crucial. And I'm kind of sad that so far yesterday and today I've been talking about components. But actually, as soon as you enter into a more dynamical view of things, you need to start thinking process. So a process view of it is probably maybe a more satisfactory or yield to more results. But yeah.
Thank you. Thank you.
If we have more questions from the audience, you can use the raise hand option. If not, I have a question myself. Okay, I'm just giving a second for people if someone wants to ask. Okay, in the meantime, I will go ahead with mine. So mine will take the conversation a bit on the other side, because I think we went a bit too much into a higher level of abstraction. So now I want to bring it down to earth with a very, very, not really controversial, but it's more of a debate. So you mentioned the necessity for benchmarking when developing cognitive models, which I agree with. It's something that we don't have. And considering the sheer plethora of cognitive models that exist, it's something that's kind of important. But this is more of asking for your opinion. What do you think would be the more, let's say, important category to focus on when we discuss benchmarking and cognition? Because in cognition, we're mostly talking about developing, the common model, about more theoretic and conceptual, let's say, element. But on the other hand, we are also, especially given the context of iCog, we want to have a cognitive model that would be implemented on an actual robot, ideally, but I mean, implemented in the real world, whereas there we kind of come to the software benchmarks, which are very different. So software benchmarks will focus on if we have memory, well, in X milliseconds we have recall, and that will be a benchmark test. If we have perception, and then we have analysis and perceptual models, what's the frame rate? They're very, very software kind of benchmarks, whereas on the other hand, cognition is mostly on the higher level of abstraction. So what kind of benchmarking do you foresee would be?
Yeah, it's a great question. And I am extraordinarily lucky that I have an easy answer and a very quick one, and it is I only have to refer you to Michael Bates's team at the University of Bremen and the Institute for AI, because that's been their entire approach. They have decided that they will demonstrate cognitive capability by getting their robots to work in everyday activities or pursuing goals in everyday activities. For example, working in a kitchen, doing the type of things that you do, laying the table, stacking a dishwasher, getting things from a fridge, doing some simple cooking. And so the Bremen team refers to they do these annual, or we do these annual, I haven't been involved in it yet, so I shouldn't say we, annual milestone events where you have to demonstrate that capability pragmatically, actively doing something concrete in a world. It's, I mean, demos are like death. Nothing focuses your mind like a demo. And it's a wonderful way of bringing things together. It's a very effective catalyst, but it's also a very good working methodology, and it's a great way of benchmarking. So if you say to someone, and also it's very become, I'll say a lot more about this tomorrow when I explain CRAM to you, but you give goals to them in a very abstract, vague way. You don't provide it in a nice pre-parsed way. So the goal would be get the spoon, or fetch the milk. Yeah, exactly like that. So, and under-constrained, under-determined. This is the whole point of the CRAM cognitive architecture. And then the robot can either do it or the robot can't do it. It can open the fridge door.
Constraints?
Sorry?
Under what kind of constraints?
So, okay, so it has a knowledge base, and that knowledge base has extensive knowledge about the environment in which it's working, right? So it's not like do it in an unknown environment. So the environment has to be known, and you have to have knowledge available to it. And the goal of CRAM then is to use its reasoning capability and its knowledge base in order to map from, I'm getting into tomorrow's talk now, but to map from this vague, underdetermined action description to the motion plan that will actually achieve the goal of the action, which is, getting the milk, getting the carton, setting the table or whatever. So not implicitly, explicitly part of the working methodology is everything is benchmarked by performing these tasks in an everyday environment. And in the future, it'll be extended to other environments, but there will be everyday environments. And increasingly in a few years' time involving people. At the moment, it's focused on manipulation.
Yes, sorry, I had understood you meant constraints as also external, not just the constraints of the cognitive model itself, but also constraints that are given in terms of either the time necessary to perform a task or the shortest path in terms of processing. Yeah,
this goes back to a little bit of Giulio's point about time. I've never been a big fan of allowing the fact that your processing speed is slow to allow you to bias your computational model. I prefer to get the model right. And if it takes a long time, then that's just life. And to be honest, I think that's pretty much the approach that Michael and his team take. So a lot of the videos are speeded up and it looks amazing. And very effective, and you think you've solved all of the problems, as Michael said, but you haven't. But nonetheless, the job gets done, the action gets executed in a world which is real and isn't necessarily constrained like an industrial world in order to facilitate the task. That's not the case. It's the same environment as a human being would work in. At the moment, perhaps not as cluttered as it should be. So I mean, imagine an obsessive compulsive owner's kitchen. That's how it works. And increasingly, we'll have more normal people, normal kitchens. But it's a very effective way of keeping the whole thing benchmarked as a working methodology. And you could bring your robot in and say, well, can you set the table? Or can you put the dishes in the dishwasher? Or can you put away the plate? Or can you stack them? These are easily replicable benchmark scenarios, which are agnostic to the underlying model, and that's important.
Yes, and I agree. I mean, time should not be the first priority in these tests. So getting a task complete, which as given in a very, very generic way, as vague as possible, let's say, and getting a model that can identify all components that are inherent in that task and successfully complete them, I think that for now is definitely the first goal. Of course, later on, if you want to have this kind of a model implemented in a physical robot that interacts with people and with the environment in real time, and not with, of course, roboticists that are very okay with waiting 2 hours for something to happen, but with people that want the Roomba to do something immediately. But that's an optimization problem for later on. I think this was a nice segue into tomorrow's talk.
Well, it is a nice segue into tomorrow's talk because, I mean, you're absolutely right. We kind of, I won't say got distracted because I don't think it was a distraction to talk about the things we were talking about earlier, these dynamical issues and the autonomous systems view of cognition. Because it's back to what I said at the very beginning, it depends on what you're trying to achieve. What are you trying to understand? But if what you want to build are cognitive robots which can work effectively and do useful things, there's an awful lot you can do, and I'll tell you all about that tomorrow. I mean, it's not my work; it's the work of Michael Bates and his team. But I'm very, very happy to do my best to try and explain how I understand it, based on the time I've spent in his lab. Because it's very compelling. I mean, it's both pragmatic and a great story. So, but wait and see. If I'm not, I hope I'm not setting myself up. No, I'm not. I know I can deliver on this one.
Your only mild, not really even problem, but something that tomorrow probably you and Michael, if he's present, will get a lot of question, is from the software engineers for Lisp. But that I think was already announced to you, that to expect people going, but why Lisp? Which I agree with you that it has a lot of advantages, actually.
Yeah, but I also believe that you should never become divorced from software engineering either. I mean, you have to remain grounded, and you got to program these systems. They got to work, So you need both. You need it all. You need the wonderful theory, and you need then its realization as in a practical system.
Yeah, it is.
And that's why it's hard.
Yeah, it is also an important exercise to find out which are the technologies that you need to develop in order to speed up or improve the performance.
Sure. Yeah.
Okay.
And if you were to build back in the embodied cognition systems, again, Giulio, this is something that you were saying 25 years ago, and more actually, about the idea that we need more work on material science.
Yeah.
So that, we need to escape from our sensory motor systems that we currently have and bring in new materials, which in a sense will help solve a lot of the problems that we now currently try and do in a computational way. You don't have to do them that way.
Yes, and the analog processing also.
Back to analog processing.
Yes. It has big advantage.
Now we're going to get accused of being old-fashioned. So
well, it comes back, I'm sure.
Yeah, it never went away.
Yeah, that's true. That's true. Okay.
Kim.
Well, Anna, if there are no other questions, I think we can free David. And
I think so.
For those of you who are not, very deep into cognition, you have to appreciate the fact that in less than 2 hours, these 2 hours spared you, I don't know, maybe 100, 200 hours of reading, because, there was a sort of a filtering out some of the important, features of a cognitive architecture. And, doing this in less than 2 hours is something that, David can do it. I don't know how many other colleagues can do that. Thanks. Thank you, David.
Yeah, thank you. But it is a subsample, unfortunately.
Well, yeah. It's always,
that's
yes.
Thanks.
Okay.
Thanks. Thank you very much.
Yes.
Okay,
Yes.
I just want to say, do come back tomorrow, because it gets better and better.
There are questions? No.
I don't think there are questions. I allowed people to unmute themselves if they want to say thank you to David at the end. And tomorrow's lecture is going to be deep into CRAM, and I think it will be very, very nice to attend also for the people that maybe are from the software or robotics side and not necessarily into cognition.
Okay. We are on the same side.
Thank you very much, David.
Thank you.
Bye.
Bye.
Thank you. See you tomorrow, everyone.
See you tomorrow.
Thank you.
Thanks for all the good questions, by the way.
Yeah, absolutely. I think it was a very, very nice discussion.
Yeah. So more of these tomorrow, and tomorrow, because hopefully we'll have some of the team from Bremen here, and if I can't answer them, I can deflect, which is I'll have a safety net. I didn't have one today.
Good.
So,
I checked out briefly people from Bremen today just to be on the super safe side to avoid the bots. So when there were people in the waiting room that I didn't recognize from iCog or from IIT, I was quickly like Googling on Google Scholar and, okay, Bremen. Excellent. So Maryland. Okay.
The team in Bremen know everything I'm going to talk about tomorrow. So maybe they won't come and I won't have a safety net. So let's see how it goes.
Bye-bye.